Okay, as I had mentioned this week, so that you have flex time, a couple of things. First of all, I'm going to do this will be a pre-recorded screencast, and then I'll also do one for Wednesday. And of course, you all have flex time to work on your exams, work on some of those assignments and projects before the final. And of course, we're coming upon Thanksgiving break, so it won't be too long before you'll have those things will come due. So I want to briefly cover that. This is Module 12, of course, and the PDC project that is due on the 16th. Okay, and that's a pretty big detail. It's a very detailed type of case, so we'll be talking about it. And then you have the Anderson tests on them, chapter 13, 14, and 15. And I also have a PowerPoint for chapter 13, and then a tree plan guide, an example, the differences between estimation, extrapolation, prediction, and forecasting, relevant cash flows for projects. A lot of information here and a lot of really good material, all in support of this one case. But we're going to see this done. Now, before we start in, I just want to quickly review the Burger King case, and so I'm going to publish the key, and so everyone will be able to see. And this is the Burger Dome case. And it's covered over on page 517 in the textbook. So we'll go to Vital Source and we'll grab the textbook. Okay. And look here at page, and I'll go back in, search the book, and I'm going to look for page 517. Okay. And it gets us over here to the operating characteristics issues. There we go. The Burger Dome case, again, we were studying waiting line or queuing theory. I provided you a lot of resources on that. And as I said before, this queuing theory, it would be an entire course if you were getting a degree in management science or operations research. People tend to put the two of them together, but they're not quite the same. So let's just say if you're getting a degree in management science, you'd have nothing but a course on queuing theory. And here in this situation, this is the Burger Dome. They have a 2-server waiting line. And as we talked about before, and I'll annotate it for you again, okay? And I'll draw this for you. Okay, move this back. This first person who comes in is taken care of by server A. Then this person comes in, they're taken up by server B. Now, at some point, one of the two of these will go on after the order is filled. And that means that the third party in the waiting line will either go here or will go here, depending upon who gets finished first. Now, if you have a standardized waiting time, service time, then what happens is you're talking about the amount of time that they wait within the system, the amount of time it takes to fulfill their order. And so this person theoretically could be waiting behind 3 orders. Now, in truth, out in the world, there's no guarantee of this. None whatsoever. But again, I think if you want to put the two opposites, one would be a waiting line where people come in to get checked out, say at Walmart. That's an uncontrollable process. You can compute all the averages and look at all the industry standards you want, all that, but it's ultimately you got people in there and stuff happens. Then you can compare it to, say, the perceived static nature of bringing cars in to get them washed. And so every car, depending upon the amount of money somebody spends, gets a certain level of service. The car gets waxed, clean, etc. So we're working with this type of situation. Of course, it's more complex. And I'm going to turn that off there because I'm finished. Well, let me do this and take that. I'll get the old eraser out here. Let's get rid of these. Okay. Very, very quickly. Now, we get them information about the arrival characteristics. We work through the probability that there are no units in the system. The math is quite elegant, again, but you can't be fooled by it because the data here, the arrival rate, the service rate for each server, the number of servers, those first two, the arrival rate of the server, arrival rate of this for the system, okay, is if it's variable. Even if it's a Poisson, you're going to have some variability, and you're going to have variability here, the service rate for each service and the number of servers. This is what you're trying to figure out in terms of the multiple server waiting lines. You get the average number of units of the system, mass all there, and they walk you through all this series of these, and we start to use probability theorems. Then we build the operating characteristics for that problem. Now here we have the values for a multiple server line with waiting lines with Poisson arrivals. The Poisson, remember, is we build up and then we flatten off, we build up, we flatten off, we build up, we flatten off, and exponential service times. Okay. And again, the exponential service times are the times between the arrivals. And they walk us through the equations again. Then we get the characteristics of this two server system versus the one server system. Okay. And we begin to see the probabilities. Nobody's waiting. One person's waiting. And then you see and remember our model, and we'll look at it here for just a second. Remember our model here, the probability of zero customers, the probability of zero customers in the system for a two waiting line is 0.45. Okay, because think about it, we have two. If we have two customers and they're both pretty much equal probability that will be served. Then when you have one person, okay, there's zero customers, it's roughly half and half, I'm sorry. And then we're looking at one customer, two customers, and notice how the probability how that probability decreases, okay, with the number of customers, okay? And so they establish this waiting line and this operating characteristics. Okay. Now the book talks about doing a short little experiment, and at the end of the day, explaining that. And we get some general models. This is from Little. That's one of the reasons I included those extra readings there on the Little's 5 equations, Little's law. Okay, and then move into the economic analysis of the waiting lines. Well, let's look at the file. Okay. And I had made the key available, if I'm not mistaken. So I'll just download it again. and we'll take a look at it. Now again, the efficacy of this, the usefulness of this always depends upon where did you get the data that you plug in. There's going to be industry data. You'll have some data that you've collected, okay, and somewhere between the two is the truth. I think that if you have industry standards of some type, you'll get a lot more signal out of a piece of data than you would noise. If you say, okay, well, we've been doing this for 20 years and we're going to take 20 years worth of values, fair enough, okay? However, is the past a prologue to the future? And you always have to ask that. Now, one of the things that you can do, again, is what I call leverage the law of large numbers, and that is you just simply say, okay, I'm just gonna I'll use the rand between tool and Excel, and I'll simulate it out using 1,000 numbers or 2,000 or 5,000. Okay. So let's look at this. And we're asked to use the goal seek to obtain a probability of O12 that an arriving customer has to wait by changing the number of servers. Let's look at this first of all. And that probability of an arriving customer having to wait is going to be cell C19. Okay. All right. And the number of servers is up there in B7. Okay, so this is going to be a simple process, and I'm going to do this. So click data, and I'm going to use the what if analysis. Here we are, and I'm going to do goal seek, and we want to change that to 0.12 by changing the cell number of servers, okay? And C19 is the probability an arriving customer has to wait, okay? And here are the operating characteristics. And we'll click OK. All right. Now, notice what's happened here. We've got this figure, all right, and we use the goal seek to obtain a probability of 0.12 that an arriving customer has to wait. Okay, and we change the number of servers. Okay, now we have far exceeded 0.12 as we put in. We have now practically 3 servers. Okay, and now we can play with it a little bit. We could put in 3 and see what we get, and then we could put. We'll go back here. And we could put the 1.8, and that's about a 50%. So we could try 1.9, and we're at about 17%. And we could put 1.87. See. Now I want you to notice something. Well, let me go back here. All right. And we're going to put the number of servers. All right. And we've got, we'll do that, and we'll do it again. And again, we can just play around this a little bit. That's the whole idea of the goal seek. And so I'm going to set this cell, C19, to 0.12, 12% probability that someone will have to be waiting. And we're going to do it by changing the number of servers. Now look what happens. Now we're back here. And we get a volatile figure, but when we go close to 3 servers, okay, we drop it down to 0.5. Now, if I have 2 servers, let's just leave it back here. So, okay, if we put just 2 servers, let's see what we get. Okay, so you can see that the more servers we add, all right, the lower the probability that a customer has to wait. It makes perfect sense. Okay, makes perfect sense. The more servers, the lower they have to wait, the lower the wait time. And think back to when we did that total cost curve. All right, the cost of waiting versus the cost of providing service providers, and we saw that the total cost, there's a point where it's low and then it goes up. We have service cost that's linear; it mimics a fixed cost. Okay, and the cost of waiting drops down the more servers we have, or the fewer the servers we have, the higher the service cost. And how we talked about, we're trying to optimize, so we try to find that sweet spot. And you'll remember that from last week. So we've worked through scenario 1. Here's the base case. Okay. And notice this one person, it's a probability of 0.12. With 2 people, okay, the probability of arriving has, let's go back here for a minute. With 2 people, 2 servers, we have a 0.20. And we're back up here, same story, okay? And we're going to do scenario 2, okay? And this is, we're going to use the goal seek again. And that we're going to try to get that down to 0.04. And that's by changing the cell, the number of servers. Intuitively, it's going to take a lot of servers to get us there, I think. I was right. It's going to take us 3 servers. Now you say, well, what's the point of all this? Well, the number of servers tells us something quite significant, and that is, what will our labor costs be? How much more square footage will we have to have a 3rd person? Okay, how much more in supplies do we have to have that 3rd person? Or deliveries, if we're running a fast food restaurant and somebody delivers stuff to us. So we have a 3rd server, and of course that and if that implies additional sales, then we've got a whole nother set of issues to deal with. So it's designed to help us understand that. And we're down close to 0.4% probability that an arriving customer has to wait. Okay, and that may or may not be good for us. It's queue discipline, and so it may be beneficial for us to have fewer servers if we can make the wait time a little more illusory, or the wait time not seem as significant as it might be. And we talked about some of that, where restaurants, they have a certain tactic to bring in and hold you there unless they can seat you immediately. And if someone can always seat you immediately, then especially if it's rush hour for them, in other words, you're at the top of that Poisson stair step, they probably are over capacity. All right. Well, that's pretty much it in a nutshell, and I'm going to close this off here. Okay. But that's the key. Okay. And now let's go back over here. That was the to server key. And we're gonna, and of course you'll have you have these 3 exams coming up, 13, 14, 15, and we're going to talk about the PDC project. Now, I'm going to open this up for just a moment here, and it asks us to get the PDC file, okay, out of the chapter, the Anderson files for chapter 13. So I'm going to diminish this for just a moment, and I've got my Anderson files. I can open it up. And there's the PDC model. Now I'm going to copy it to my desktop. All right. Now let's open it up. The PDC model is a decision-making model. And the textbook, and this is over from chapter 11, right? And pardon me, chapter 13 files, chapter 13. And this is the reason that I provided you the PowerPoint, because it's going to give you a very nice, succinct overview of the PDC project. Now, chapter 13, pages 618 to 35, provide the whole thing. So we're going to go over here, and I'm going to look for page 618. I'm going to look at decision making, okay, under uncertainty. Now, as I've said before, when I talked about the queuing problem, there could be a whole course over that. I can tell you for sure that with decision making, that the whole decision making is a science as much as an art, and an art as much as a science. And I can assure you that we try to utilize tools to help us. Now, here's the most basic tool that we use when we talk about working with a decision, okay? And what we're looking at is just, this is the end game in terms of a maximum regret, okay? Where we try to minimize our maximum regret. In other words, we try to cut our losses. Now, here's decision making with probabilities, and it gives us some of the theorems for that. The states of nature, the probability that they'll occur. This is a lot like a weighted portfolio. And we'll pop over here to the next, and we start to see the expected values. And in your finance course and in stat, you should learn about expected values given a certain state of nature. In this case, I think they're talking about building a hotel or housing units or something, and they have 2 scenarios. One is, I think, strong demand, which they think is about 80%. There's about an 80% likelihood, and then there's a 20% likelihood, they believe, of having weak demand. Okay. And so this starts us on that road of decision making under uncertainty, and we're going to learn about. We're going to see the decision trees. Well, what a decision tree does is it lets us take the decision, the permutations or possible outcomes of a decision, and illustrate them quite well. Now, there are things out in nature that illustrate this. You say, what are you talking about? Okay. I would venture to say if you really looked closely at say a bunch of fall foliage, you're going to see some of it that's dominated by one color, some will be by another color, and that's because of different conditions in different trees, and as those branches go out, they don't all get the same type of sunlight, etc. So here's a situation where we're using a decision tree, and in this case we're looking at small, medium, or large, and this is the demand, okay, for a particular product or whatever they're going to do. And they're saying if the demand is small, then the expected value is 80% of 8 and 2% of 7, which gives us 7.8. That's our outcome. If the demand is medium, okay, then we get 80% of 14 and 2% of 5, and then we get 12.2, and then the large you can see is 80% of 20 and 2% of -9, and we end up with 14.2. Okay, so the decision tree is just a way for us to put this into to visualize the data a little easier. There's a nice case under here, and this involves the oil business, and I think you'll want to take a look at that. When we begin to talk about the expected value of information, of perfect information, and we can compute that. And then here's our payoff. Now, you've often seen me do this very same thing when I've set and I've drawn a square with 4 quadrants, and I've put condition 1, condition 2, response 1, and response 2. No different here. I've never used this little dual, so let's see what happens. Oh, I got a little bit more freedom here to make it look really splotchy. Okay. Here are my decision alternatives. And here are my states of nature. Okay. Now, you've heard me talk about this many, many times about type 1 versus type 2 error. Type 1 is a false positive. We think you have cancer. Then we find out you don't. Or a false positive. We don't detect cancer, but you actually have it. And so doctors have to be exceptionally worried about false negatives, okay? And that's why ultimately they may have to do any one of a number of things to find out what's really wrong with if you indeed have that problem. So we have these type 1 and type 2 errors, and we balance them off. And then there are those situations where we make the correct decision, and those times when we don't at all. And so we have some decision alternatives. We have 3 of them here, okay? And we have our states of nature. The demand is strong, or we have weak demand. Now, the one thing I don't like about this, okay, is that we're given, again, this kind of binary choice. The decision alternatives here are fine, but they are infinite. The states of nature are fine, but they are infinite. And so, as I've said before, decision making produces a continuous curve. It's not bimodal. It's not right or wrong. It's really, really right or really, really wrong, or kind of in the middle. And so they show us this in the condominium project. I really encourage you, to take a look at the PowerPoint from 13. I think this is exceptionally important material for a very simple reason. It's about decision making. And if you can start to think, if you can train your brain to go, okay, my decisions runs along a path of alternatives. There's not one right answer or one wrong answer. And the outcomes I can get can range from really good to really bad to okay. And so we attach probabilities based upon experience, based upon past, based upon maybe industry standards. Some kind of forecasting has been done. Actually, when we do a table like this of expected value, we're engaged in forecasting. And so you can see state of nature versus decision alternative, how we end up. Now, for example, if we say, let's build a large complex and the demand is strong, we're winners. We're going to make 20 million or whatever we'll make, 20 million. If we think, if we say, hey, we're going to build a large complex and we have weak demand, notice what happens. We lose 9 million. Okay. Now we may have the 9 million to lose because we may know that if we build in stages, okay, then I can parse this through. And the truth is, in a situation like this, it's not really too different than what's going on out west of school there. If you drive by, you'll see that housing development that's right across from St. Gregory's. If you drive on back in there, you'll start to see that the developer is taking it a chunk at a time. Okay, and we really do have to remember that it's the range of outcomes. Okay, the states of nature and the decision alternatives. The decision alternatives and the states of nature, there are going to be those times where we don't know what to do, or those times where we're really not sure what's wrong and how to fix it. Well, all that being said, we'll forge on through here. And let me get my trusty annotator out and get my eraser. Okay. And again, we start, and they have us look at the expected value perfect information and strong and weak analysis. And the book then begins to walk us through risk analysis in terms of sensitivities. Okay. And looking at these from various deterministic outlooks. And then decision trees, and that's where we start. Okay? And notice that we have, and this is doing a market research study. Now I want to go back up here for just a moment. Here's what we're asked to do, and we'll talk about this some more on Wednesday on exactly what I'm after. But I want to go back over here for just a moment and walk you through. There's a tree plan guide, which is what we're working with, and a tree plan, there's an example for you to take a look at. All right. Then I also have some stuff in here about capital budgeting. Okay. And I want to talk for just a couple of minutes or so as regards this resource, the difference between estimation, extrapolation, prediction, and forecasting. Now, estimated, as he says, is a calculated approximation of a result. Could be a forecast, but not necessarily. Then we come to extrapolation. And And this is estimating the value of a variable outside a known range of values. In prediction, we're saying something about the future. Forecasting is the process of making a forecast or prediction. And so we go from, okay, just simply making an estimate to extrapolating out past known data ranges. And as you note here, predictions are usually focused on outcomes, not pathways. And then we talk about the pathway as well as a prediction, and that's forecasting. And it's an excellent, excellent resource for you to take a look at and to really chew on. Now, and I'd ask you, in the PVC project file is over there in chapter 13. Now, another resource that I brought in here for you is what we call the relevant cash flows for a project. And this is from the Student Accounting Association. And so well, you need to understand the cash flows that are relevant or are not relevant to a capital budgeting project. Because where we've been talking about building apartments or things of this nature, we're really talking about a capital budget and capital budgeting. So it's good for you to, I'm sure you probably were exposed to some of it in finance. And I can tell you again, capital budgeting, here would be another entire course you could take. I know I took 2 of them, okay? And understanding the relevant cash flows for a project takes some work. So there's a resource for you to take a look at there. Okay. I want to go back up to this market research, and this is includes the market research. So they've done some market research, but notice how remarkably it's like a set of permutations. And if you took this and you took it counterclockwise, you'd see it looks like a set of branches, because it is a set of permutations. It's our interpretation of the fork in the road. Will it go left? Will it go right? Will it go north? Will it go south? Will we go east? Will we go west? And so when I've said to you before, decision-making isn't binary in nature, it's continuous in nature. Now I think you can see what I'm talking about, because you can see all of these possible outcomes. And we can just build on these and build on them and build on them. The law of large numbers will at some point get us what will actually happen, if we can ever go that far. But we can't. Okay? We can go to the law of large numbers only to a certain level. And then there's a point where it's beyond our comprehension. It's beyond our computational skills. And there's only one person who knows and understands all that, and that's God. That's why God can take things that look like they're just completely crazy and turn them into something really good. Okay? Because he knows all. I mean, he knows how this whole tree is going to work out, because he created everything. Well, you could see here from this from this tree, okay, that we're looking at the expected values of these decision trees, and they're going to give us a market study if it's favorable or it's unfavorable. Now, what they don't do is tell us that most market research studies are not favorable or unfavorable. They're typically, well, I'm kind of favorable, kind of unfavorable. And that's how we hedge our bets. When you get that kind of response, that's somebody trying to leverage the law of large numbers. You know, and it's like I said, I think in class last week, if you go to a Lake Eufaula, you probably will not catch a swordfish. You could go 100 years and probably not catch one. You go to Lake Texoma, I don't think you're going to catch one. But if you go into the Gulf of Mexico, you're going to catch one because they're out there. And it's the law of large numbers. And you go enough times and you'll get one. So we'll be working with that, and I'm gonna have some variables for you. And notice here's the tree with branch probabilities. Like I said, this is the stuff of a whole course, and they give us the decision. They give us the expected value by each node. They say, oh, this sounds a lot like a network. Yes, networks, when you hear people talk about a neural network, what they're really saying is how people kind of extrapolate it out here, because these are extrapolations usually. And I brought it and I came up with some kind of value. All right. When people play roulette, or games of chance, they choose a number. They choose they try to play a certain set of cards, and this is really the heart of decision making, and how it gets done. And we see that they have these expected values, and they work backwards from them to these different nodes. And again, here we are comparing expected values at chance nodes 6 to 14. And here we are, we look at the two best decisions at node 3, 4, and 5. And we reduce it to 2 decision branches. And we come to an optimal decision strategy. That shows us the risk profile. Now, Bayes always rears his ugly head. And so we see a Bayesian analysis. And here's our market research again on those conditional probabilities. Now, this little blurb right here, I think, let me go back here, is really good because they talk about false positives and false negatives. And so if we have, it says a favorable market research report given the state of nature is weak, demand is often referred to as a false positive, while the converse an unfavorable market research report given that the state of nature is wrong, strong demand is referred to as a false negative. You can have a situation where here we see that we thought we'd have weak demand, okay, and we end up with an unfavorable result of 0.75. So you can see these permutations as they work themselves out. And this shows us how to use branch probabilities, looking at joint, conditional, and posterior probabilities. And I'll let you wade through that a little bit there in the textbook. And utility and decision. So the model is pretty versatile. You can put it through all kinds of plug in all types of data, and run expected utilities, values, all those kinds of things. Okay, so the text is rich with all of these kinds of sets of data. The thing that I want to do for you here is to just give you this simple model to work through, okay, and also expose you to some to expose you to some nice resources that help put some of this information into maybe a richer context for us. Well, that's pretty much. We'll look at PDC and we'll talk some more about the tree plan and tree diagrams and all that. And this is, as I promised you, I am going to do. I did a. This is for Monday, and as I promised you, I did a pre-recorded session, and then Monday, which is supposed to be bad, that's tomorrow, bad weather. That's going to be a virtual day, and then Wednesday will be the ground-based day. So back over here, and I'm going to stop the share and then stop the recording, and I'll post this. And I think, if I'm not mistaken, before I do this, let me go back up to the announcements. I think I do have a screen. I'm doing the pre-screencast, okay? I've got my schedule here. Yes. During class time, when we have these flex time weeks, as you're working on projects and so forth, I'm going to do a pre-recorded screencast and I'll post it. But then I'm also going to be available online in case during that class time you want to come and ask me a question. And then you have the rest of my schedule for where I'll be. You have the rest of my schedule for my office hours, so it shouldn't be hard to track me down. Okay, my friends, I'm going to stop the share. And then I'm going to end the meeting. I'll stop the recording and then end the meeting.